my very low technology Blackboard about what I've seen. So as I've done in the previous one, I essentially went through what has been discussed and taken some of the things which I thought more interesting. You know, there are always a lot of questions like, oh, this code doesn't compile, and then there is something we can fix. But these are like the questions I found which are interesting. So and of course, just to remind everybody, there is this questions and answers thing in Zoom. So if you have any other question or anything you would like to discuss while we are talking, just feel free to write there, and actually it's quite nice because then I can see them and sort of manage them. So but well, this time there has been like several chapters spawning many different areas. So I always want to think that like the other chapters are like preparations, like things you need to know for Haskell, and now it's the part where you actually learn the usual stuff, how to build things with Haskell, how you do databases, how you do concurrency, how you do things like that. So I mean, I hope you liked it, and then you've started to see how you can build an entire application using Haskell. You know that's actually the case, that you can do your I/O and your databases and everything, like in most programming languages, to be honest. So in all of this, Haskell is not so different, except of course that you need to usually use I/O or a monadic stack to do all of this. But well, here is the the things I wanted to talk today about. So I don't know. So I talk with the type of bit that maybe, well, there is a chapter in the book about testing, but there were also some questions about testing. So you know, that depends whether you like me to talk a bit about this or not, how the testing ecosystem looks a bit in Haskell. But anyway, the first thing is this 3 points about parallelism and concurrency. So this chapter about parallelism, concurrency. So I'm never 100% sure about how people use these words in the book, and how I often have been told about this is that like parallelism is about doing many things which are independent at once. Concurrency is where you need to you actually need to have some sort of synchronization between them. So the usual case of parallelism in Haskell would be like a parallel map. So that's like something that, because of purity, we know that when we are mapping over a list, it doesn't really matter which is the order in which we do, or if we have 5 different processes doing the things, because of purity, there is no side effects we can see apart from the computation itself. So we can just, you know, put this running in several threads, and that would be okay. Which is different from concurrency, where these things need to have some kind of synchronization. For example, well, you have some kind of, let's say, message queue, and then of course the different threads needs to communicate. You need to have you know, somebody will have to ask for information. Then you have the workers. The workers may need to maybe are synchronized by some kind of broker, which is the one which tells each worker what to do. So there is a lot of synchronization. That's what is often mentioned as concurrency. So the thing is that when you learn these things in most programming languages, you just essentially learn concurrency, because given that you always have the ability to do side effects, then parallelism is usually more hidden. But given that in Haskell you have all this purity, then there is all these nice things you can do. And then you've seen that, for example, there is this kind of monad from which you can escape, which is this par monad, where you have this run par, and then you have par A to A, where you essentially say how you want to do your you describe how your parallelism looks like, and then these things execute this. And because everything is pure, we cannot really see the effect of doing this in parallel or not, except for the fact that hopefully it's faster. So I wanted to go actually around a couple of packages, which I think are nice to. So let me see. So there is this. Let me see whether I'm. Yeah, I want to share Firefox. So let's see. Here we are. Yeah, these are the different. Well, this is one of the parallelism libraries. I wanted to talk also about this Ulvish, and then there is yeah. So I don't talk about all the Haskell libraries about parallelism concurrency in the book, but I wanted to mention roughly the three things which I think are interesting. So monad par is like the simplest, where you actually have to essentially describe the data flow, and then it roughly creates a thread, one of these green threads, which is very cheap for every computation. And then the way you do this, the way it does is that it knows what are the dependencies between the different things, like here, B and C depend on A, which you write like this. So you just get whatever this A is, and then it ensures that it works, well, hopefully faster. So the good thing about this is that for most people, this is quite similar to other things, like, if you do JavaScript, this looks very much like promises, for example. So you essentially say things which you want to execute, and then, under the hood, these things are just executed. There is this, and what I wanted to mention about monad par is that by default, there is this run par, and this run par, as I mentioned, is what allows you to run this in parallel. But run par is not the only way to do this. You also have these different schedulers, and these different schedulers can be useful if you want to have a bit more control about this. So I just, essentially, I just wanted to mention monad par. It might look that, well, you have no control about the actual amount of parallelism, because that was one of the questions, how do you control this parallelism? Because it just takes this par and magically executes the thing. But you actually have different schedulers to do this. Another different way to work with parallelism in Haskell is to use this parallel package. And this parallel package is it's something which comes with strategies. And actually here you are a bit, you say what you want to do a bit more explicitly than before. So monad par is supposed to be like, okay, things just happen under the hood and you only say what are your dependencies. Parallel actually allows you to say exactly how you want your computations to be done. And I'm mentioning this, as I said, because in the Discord group, there was a question. Okay, imagine I want to run things in parallel, but I just don't want to break. I just want to execute 5 elements from the list in the same processor. So how do I do this? So I'm not sure whether monad par allows you to do that fine-grained thing, but parallel definitely allows you to do so. So what you do is you create strategies, and strategies is about how you evaluate things in different processors. So for example, you have part traversable, and that's a strategy which takes another strategy. So there is all of this is very compositional, and then uses this strategy on each different element. So you can have, let's say, traversable could be, for example, a list, and then you have list of tuples, and then you have a strategy which says, okay, evaluate the 2 things from the tuple in the same processor, and now create one thread for each element of my list. But then every tuple is just done in the same processor. But you have here a lot of these things. So for example, you have a val list n. So you evaluate the first n element, but you also have like a par list chunk, and then that divides list into chunks of the same value of this int value, and then it executes the one strategy over these chunks at each time. So that gives you a bit more fine grain. You can be a bit more explicit, but of course that means also that you have to be explicit. So your code no longer looks like, okay, I'm just executing stuff. You actually need to specify those strategies. If you don't know about this, there is this book which is awesome, written by Simon Marlowe, which is like one of the main writers of the GHC compiler. He's mostly worked on the modern runtime system. And he's written this book, which is freely available, Parallel and Concurrent Programming in Haskell. And if you want to see, that this is something which is, it's really great to read, because he doesn't just talk about, well, I don't know where you can get it for free, but I know it's free somewhere. He doesn't only go about how you work with this in Haskell, is that actually he starts with this eval monad, which is something simple to understand, and then he sort of from this grows the different mechanisms in Haskell. So you can see that Haskell actually has a few primitives, and that on top of it there is all of these libraries. And I wanted to finish with some library which I think is a bit more advanced, but I think it's also very cool. So when you use monad par, you use these things called ibars to communicate about things. And ibars are essentially like, thing like promises, things which are either waiting or are fully fulfilled. So everything you can do on an ibar, that's essentially, well, you wait and then you block on it, and then when it's done, and then you get the whole result. But that sometimes is not perfect, because imagine you have one process which is producing values, and then you have your other process which takes this list of values and also does, some kind of map or fold over it. Well, the second process can already start executing things when the first one, even when the first one hasn't finished yet, but has produced something. And this Elfish is taking this idea and turning this into an actual programming model where they use L bars. So that's like the next I bars, And the things about L bars is that it's what they call they grow monotonically. So there are things which always grow. So imagine you are producing a list, and you are producing the list, and then you are producing elements and elements and elements. So there are things where you never can go back and unproduce things. So for those things, as I said, if you are producing a list and then you are consuming the list in order, then you can start your second process when the first one starts just producing elements, and then it has a bit more synchronization. And this Elvish hides all of this. So they have all these different data structures. You can use in this way. So you have ibars, which are like the simplest things. So you can think of ibars as a maybe. So it's either there or not. But then you also have like maps and sets, as I said, things which always introduce anything. So I just wanted to mention these things because, they are part of how you can get a bit more control about how your concurrency, well, not the concurrency in this case, your parallelism is done. So you are still working on this idea that everything is pure, and thus you can just execute things in different things, but you can have a bit more control if you decide to use parallel because you have a strategy, or you can use Elvish to not block until some things are done completely, but until things start to be produced. Cool. So yeah, I don't know if you have any more questions about parallelism and concurrency in GHC. That's more of this is just for GHC. Otherwise, I'll keep talking about the other things, and yes, if you have any questions in the meanwhile, just write it in the Q&A thing. So maybe good. So another question that was raised is that, okay, last time we talked about alternative and monad plus. So if you remember, monad plus was this, let's say, so alternative A was this class where you had empty, let's call it F maybe, and this thing if you remember, I didn't know how to call, that's something like or, and and this is different from monad error. So monad error gives you something different, where you actually have let me remember monad error. Let's just copy it from here. So throw error and catch error. So you have these two things, and the question was, okay, what is the difference between these two things, and when should you use one or the other? So the main thing, there are like so the conceptual idea is that you use alternative or monad plus, which as I mentioned last time is just like alternative plus monad. So when you have a notion of failure, but this failure has no information attached to it, then you also have a way to recover, but the only way to recover is to sort of try something different. And that's quite embodied by for example, the instance for maybe. So if I write the instance of alternative for maybe, then my empty is going to be nothing. And if you see, it has to be some m of a, so it has to be some maybe of a for any a I have. And then this or was, well, if I already have something, then I don't want to do anything else. Otherwise, I'll just go and try the other branch. But this is, you know, you have essentially no control about when this thing is taken, other than you know that this has failed somehow. Monad error is more similar to actual errors. So when you throw an error, you actually have information about the error E that you are throwing, and you also, when you catch the error, you see here you don't have MA and MA like this is like above, but then you also have this E passed as information. So this, I think this is more similar to like an exception model, for example, where you can throw some kind of exception and then you catch it and then you have information about the exception. So of course, for example, something you can do is give give an alternative for either E, okay, which looks pretty much like the one before. So if I'm right, then I just get it. If I had the left, then I try the other thing. But you have the problem. Okay, what do I turn as empty? You know, I have here left, but I don't know what to write here. So what people usually do is they just require to have a monoid here. But well, the idea here is I just wanted to mention that if you have something like either, this doesn't fit this idea of alternative so well. You can make it work, but then you need to require this thing, and the empty has this left or some value, which is kind of just one default value coming from E, but you know, does it really represent something meaningful? Whether if you have here a monad error E for either E, this looks much nicer because, well, you throw error and that's, you know, that's left. And if you catch an error, well, if I have a right X and I catch an error, then, well, I don't care, that's a right X. If I have a left error and then I catch an error with something, then I pass this this E to the next thing. So this is really like a handler. Let's call it H because it's like an exception handler. So so that's roughly the the case. In practice, what I often do is, well, I almost never use alternative except for a few cases which I know, which is like maybe for validation and using lists where I want to get a set of values, but I, you know, it's like a different thing, which for me doesn't talk so much about errors themselves. It's more about different ways to do things. That's, like I said, like a validation. So whereas monad error is really like the kind of errors which look more like exception, where you have a domain where you have some errors, and then you want to be able to figure out what these errors are and do something in response to those. Hopefully that made the difference clear, and well, otherwise you can look at the different ways the throw error and catch error differ from empty and OR. Okay, so the other thing with I've seen been discussed is that, well, when you define an exception, then it's very weird, but you just say instance exception my exception, and that's everything you write. you can actually write where if you want, but that's exactly the same. So that raises the question that sometimes you have empty instance declarations. So how do they work? So this is not, some of these are only discussed later on the book when we talk about generics, but I wanted to give a rough idea of how all these empty things work, which is actually the fact that they are empty is just like extreme case of the fact that you can forget about some of the methods and they will be written for you. So let's start with this typical example, which is a clause like EQA. You know, if you look at the definition of EQA, well, you know that you have the equals, but then you also have the non-equals. So in theory, when I'm defining an instance for EQ, let's say EQ A, EQ maybe A, in theory, I should just write down both. So I should write this, nothing equals nothing, and yeah, that's true. And other than that, everything is false. And then I would also have to write the other thing, the non-equal. So I will have to go and say, well, nothing is different from nothing. That's false. Just X is different from just Y. That if X is equal from Y and any other thing, it's gonna be just true, which is essentially like, you know, if you do this, you know, nobody's gonna write this because, well, you just see that this is exactly like doing the thing before and doing the not. So you just say, okay, X is different from Y if not X equals Y. But because everybody can do this, well, the designers of Haskell thought that you can have default definitions. So this actually can be written here above. And then that means if there is no explicit declaration of the not equals, then this one is going to be sort of copied over. So you can imagine that well, this is how EQ is actually defined, and you don't define not equals, but it doesn't matter because every time you don't define it, then DHC writes it for you. So what exception does, so the trick with exception is that actually exception has only one thing, which is display exception, which takes this A to string, and display exception by definition is show. And because there is only one single method and it has a default definition, that means that when you write an empty instance, well, you actually are defining all the methods, but you're just by copying the default one. So that's where the trick comes from. Now, empty instances may come from other place in Haskell. So that's essentially what I explained until now is what makes exception fly. So there is just one single method and it has a default definition. If you don't write it, which means writing an empty instance, then it just uses it for you. Now there is something else which DHC has, which is called default signatures, and that's a harder part, but that's only usually used in combination with what we call generics, which is this ability within Haskell to write functions which depend on the shape of the data. So if you have things like EQ, you could also have a default definition for equals, but of course it cannot just be a normal definition. it is a hard definition where you say, okay, check the types, check whether they have the same constructor. If they don't have the same constructor, then they are not equal. They have the same constructor, go through every field checking for equality. And you can write these things within GHC, this idea of checking the constructor, and it's actually type safe. So this is what we call generics in Haskell. In the book, I think it's chapter 16, there is an introduction to this. Otherwise, I've given a lot of talks about that because that's like one of my favorite parts of GHC and something I've been working on for a few years. But anyway, that's where the other things come from. So for example, and these are slightly different. These are sort of default definitions which are restricted in their type. So they don't apply every time. They only apply where some constraints are satisfied. So for example, when you have this EQ, you have something roughly similar to this. So you see, this is like the type we had before, but I added these extra things. And that means essentially, well, if your type has this thing, satisfies those constraints, then you can use an extra code. And in this case, well, you don't actually need to understand how it works, but the point is that there is a default definition which uses this from, which is coming from this generic library, and this GQ, which is like generic equality. Doesn't matter. The whole point I wanted to make is that there are also something called default signatures, which allows you to say, okay, if you don't write your equality, but your type satisfies these things, then use it. So it's like a, it's an additional thing over the default declaration, this default definition. So this means use it every time it's not written explicitly. This means use it every time it's not written explicitly, and these constraints are satisfied. And if you have an empty instance, most of the time this is the case. So if you, for example, write this empty instance to JSON of person, and you may have seen this somewhere in the book, or you will see it later, in the JSON library, and it's empty. This is actually using this generics idea to write down the instance for you. Good. So that was about empty instance declaration. The other thing that was mentioned several times is that sometimes you get terrible error messages when you start working with these complicated libraries like Conduit, and we had here a couple of examples using from Conduit. And the question was, is there any sort of heuristic? How do you manage to know these kind of things? So you see that in both cases, the error reads about ambiguous type variable, M0 arising from the use of blah, 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 blah. Or here, ambiguous type variable arising from the use of blah, 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 blah. So let's see what this means. So the idea is that the idea of ambiguity is that sometimes you don't know what a type is, and the typical example of doing this is, okay, imagine I have this kind of stupid idea. I'm gonna have there is these two functions in Haskell, one which is called show, which takes requestion A and turns this thing into a string, and then there is this read function that are this read may, which is the opposite. So it's a way to get a string and read it into an A. So for example, you can use read may of the string 5, and hopefully if you ask this to be done as an integer, this will end up as the number 5. And if you try to read may a as a, sorry, you will have a maybe integer. So you will have a maybe integer. So this thing will return nothing, and this thing will return just. So these are like the converse things. So one allows you to show as a string, the other one is like a small parser, and this is why you often use read, is because in the same way you can derive show, you can also derive read. Now imagine I write this function. I write this stupid function string to string, which takes takes a string s, and then reads it, sorry. So this will return, this whole thing will return, a maybe of a, and then I show it. I need to fmap over it because it's on a maybe. So this thing will essentially take this a and show it. Now, if you try to write this, if you try to execute this in GHC, not in GHCI because something I'll explain later, you will get an ambiguous error. And where is this ambiguity coming from? Well, this read may works, returns a maybe a, and this show actually takes this a and turns this into a string. But the compiler, from what you've said, cannot figure out what this a should be, which of course makes a whole difference. So if a is an int, that means that you can read things which look like numbers and then show it back, okay. But if this a was a person, then, well, you will have a 5 and it cannot be parsed as a person. So what the choice of a is actually affects execution. So this a is not something which is not important. It actually is all about what you mean here. But there is nothing which tells you what a should be. You know, this just says a string to maybe string, and there is nothing to tell you what this a should be. Of course, if I wrote here, this should be done as maybe integer, then this is okay because this a is known, is integer. But if you have it like this, then you don't know what's going on. So the compiler cannot figure out what's going on. And it says, well, this type variable is ambiguous, which means I don't know what it is. Because I don't know, I cannot keep compiling your code because, well, I don't know what code to generate. You know, what should I do here? And this is what it's happening in all of these cases, except that it's a bit more contrived how you get to it. So let's see. The first one says ambiguous type variable m arising from the use of this pipe operation. So what happens is, and this is something which has actually been changed since I wrote the book, this run conduit res, let me find the type. This run conduit res has a very polymorphic type. I'm gonna write it here. So run conduit res has this type. Okay, it says, you know, give me a conduit over any resource, the m, and I will run it. Or this m can be any monad will support this monad unlived IO. And I'm gonna talk too much about that because I actually had to write a book to explain these things. So, you know, if after this book you want to read another one, there is this beautiful book of monads, which you can read, and there is a whole explanation about how this works. But the point here is that this m here is not fixed. So in previous in previous iterations of the library, this was actually IO. And then if you have an IO, that's great because you know everything. You know the type. If we look here, we know the type R because the result of sync file, it's gonna be a unit, and we know that this is gonna run in IO, which is the monad here. But that's not what we have in the library right now. We say that this conduit runs over any monad, which is then wrapped in resource. And well, how is it going to know in which monad this is running? Well, there is no information here because everything, sync file, blines, and source file are polymorphic on the monad. So source file also works over every monad which supports IO, the same as sync file, and lines, which is just a pure operation, just works over any monad. So the point is that by doing this, you are not fixing what this type M should be. So run conduit address says, well, I don't know what M should be. So I don't know what to run. Because of course, depending on which monad you choose, you might be doing different things. And that's again what it's saying here. And this the thing is very long, so it tells you where you are. Relevant bindings include this thing, and then there is all these instances, which I don't know which one to take. I often just don't read these things, to be honest. I just like blah, 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 blah. To me, it is like blah, 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 blah. The important things is these things. And then it also mentions something about user type annotation to specify what M0 should be, which is what I've done here when I wrote maybe int. So this is the, and here this is quite similar. So this lift is also a very polymorphic operation. And this is telling you, well, this is very polymorphic, but unfortunately, I don't know which one I should choose. So how do you solve these problems? So let's start by run. So let's look at this problem, which I think it's the easiest one to look at. So what we said is that run conduit res doesn't know what M should be. So what we could do is, the easiest thing is to write a type signature and a type annotation. So you know that this will return some M of error, and that M is what is not known. So what we can just do is say, well, this is just returning IO of unit. And by doing this, I'm fixing what M should be. So if I add this signature on top of the definition, you no longer get the error because there is no ambiguity. You know what M should be. It should be exactly IO. Another possibility is to acknowledge that you want to be polymorphic. Then what you need to write is say, okay, right, yes, I want to keep my function polymorphic. So I'm going to say it works for, I'm fixing my M, which works for monad and lift IO M. And then it knows that this thing is not unknown. It's just something which is going to be provided later. This is, of course, something you cannot do here because this A is completely gone. But in many cases, you can actually prevent the ambiguity by, as I said, acknowledging, yeah, this thing is ambiguous, but it's going to be told. It's going to be told later. But without I don't want to get very technical, but when you have a thing like this, you don't have a type signature. GC has to perform something called, oh, sorry, yeah, there is an example question. So, oh yeah, the depot asked whether it should be IOR instead of IO unit. Yeah, yeah. So if the thing is, if I write IOR here, this is not gonna work because I also need to, so monad run conduit res in this case is gonna be run with a specific value for M, but also specific value for R, because the result of this whole pipeline is not of type M of R, is of a specific R, which is the result of syncing the file, which is, so sync file is something which it's a conduit T of blah, 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 but has a specific output, which is unit. So I need to specify both. If I wrote IO of R, you will get an error saying cannot match unit, which is the result of sync file, with R, because if you write R there, that means that this is polymorphic. So you really need to fix both. Yeah. Okay, so I was saying, yeah, technically the problem is if you don't write these things, what GC sees is that there is an M of empty, and then there is a step called generalization where it tries to figure out what are the things here. So maybe you've seen that if I go and write in GC something like, I don't know, F equals +5, you will get a type like this. So you will get this type. So it performs, it sometimes figures out what these constraints are. However, yeah, so for mostly technical reasons, this cannot be done every single time. And there is, if you really want to read about this, there is a huge paper which describes how the type checker of GC works. That's called outside in X modular type inference with local assumptions, I think, by Bitiniotis and Peyton Jones, and I guess Weyrich and Sulzman. I don't remember exactly, but this describes, it's a very long thing which describes how it works, and then they talk about what they call non-generalization and why you shouldn't figure out this type. So it you know, theoretically you could figure this out, but there are reasons why you don't want to do this. Cool. So that's everything that was on my menu. I don't know if you want to, maybe I can, you know, there is a testing chapter in the book, but then let me just use a couple of minutes to talk about the fact that there are like two kind of libraries in the Haskell ecosystem. So you have these libraries like QuickCheck or HUnit, and that's how you actually define tests. So HUnit is just your normal unit testing framework. Then there is this QuickCheck, which is uses randomized testing or property-based testing. So you say something which should be satisfied by your program, by your function, and then it generates random data and checks that these things work. So it's like, you know, unit test, but 1,000 times. And then the trick is that you just specify what should happen. You don't specify the exact output, what should happen. So these two things, QuickCheck, HUnit, and other one is called SmallCheck, is how you actually define your things. But most people don't write these things directly. They use what it's called like a unit runner, a test runner. And the most known are HSpec, that's similar to like Ruby spec and so on, and Tasty, and those are just ways to put like the test together. So this you define, that's how you define one single test, and then with HSpec or Tasty you actually define a group of tests and you know, groups of tests, and they provide ways to run just a subset of your tests and things like this, or to put the output in JSON or something like this. So you know, what for example, I usually do is I use Tasty in combination with QuickCheck, because QuickCheck sort of subsumes HUnit. So I just use tasty to like put my tests together and then quick check to do this. Good. Oh, I see a question which I don't actually understand completely. So thoughts about brackets. From experience, it seems it leads to nested code. Sorry, I don't completely understand what you mean by brackets. You mean just like the angle brackets, or like, oh, you can give me a hint?
There's a bracket function. It's like a pattern where it's for resource handling. So
yeah. Okay. Yeah, you mean the bracket function?
Exactly. Yeah.
So there is this bracket function. Bracket. Let me. It's in control exception. So yeah. Let me. I'll just show my. So yeah, this is the bracket thing. So this bracket is essentially what we use, like, it's like the typical kind of try-catch final. I don't know how. Yeah, I can see. So we have try-catch finally, but essentially you have a way to get the resource. You have a way to release the resource, and then you do something with it. And this takes care to do this correctly. Yeah. So of course, the problem is that bracket has, when you need to have two resources, then you essentially have a bracket and then a nested bracket and then a nested bracket. So there are two ways to fix this problem. I think I've also reading about it somewhere. So one is this manage monad. So there are like two. So there are two problems when you use bracket. Problem number one is that bracket leads to nested code, but then there is also another problem, which is that because of this nesting, you can only release resources in reverse order in which you acquire them. So depending on what problem you think is the worst, you actually have two solutions. So one is this manage library, and this manage library allows you to write this kind of nested things in a linear fashion, and it uses some cool tricks there. But essentially, you start with this. Imagine you have this with file. And this with file is just an application of brackets. So you can see here, like with file is just a specific case of bracketing, which you know that your acquiring resource is opening it and closing it is closing the handle. So this is really like bracket. So what this library does is, by using, as I said, several tricks, it allows you to write it like this way. So you wrap your bracket things into manage, and then the other one in another manage. So you are acquiring two resources that would lead to two levels of nesting here, but here you are just linearizing it. So the only caveat is that you need to write manage. Well, that's not so problematic. And then the rest of the things have to be wrapped in this lift IO, because you are not really in the IO monad, you're in the manage monad, but you can do things there. So that's like to solve problem number one. So if you really are just worried about this nesting thing, you can use the manage thing. However, I would actually argue that it's better that you use this resource T, because resource T is it's like manage, but it allows you also to allocate and free resources in a different order. So let me see, is there an example? Yeah, so let me see if there is an example here. Essentially, resource T works like this manage thing. When you call allocate instead of manage, and you say how you allocate and how you free the resource. So it's essentially the same thing as you did before with manage. But the trick is that it doesn't only give you back the resource, it also gives you what you call a release key. And this release key is a way to early release the thing. So by default, everything you allocate with allocate is released deallocated at the end of the block. So when you run resource you allocate whatever this is, and then here at the end, at the end of something else, this is freed. But you can also release it early by calling this release function. So that's and this is often what I use and what I suggest to people. Manage is great. I like it because the documentation is awesome. But resource D gives you, solves both problems. Solves the problem of allocation without nesting, but also the problem of possibly releasing things. And it's often the case that you don't want to really, I don't know, imagine you have a pool of connections. You don't want to deallocate the connections in the same order that they were asked from the pool. So yeah. So that's yeah. Don't use bracket. Just use resource D, and you'll be happier, and your code will look nicer. And actually, bracket has even more problems. So if you ever get to read or see things from Michael Snowman, he actually has very good talks and very good information about why the bracket function is not working correctly because of something called asynchronous exceptions in Haskell. So he has written better things, and actually resource D is his work. So just use it, and then you'll just write better code. So that's it. I don't know if you have any more questions. That everything I wanted to tell, and then something about bracket. So